Watch the transfer of energy. A glowing metallic sphere hits cold water, and the reaction is immediate and violent. What you're seeing isn't a physical substance leaving the metal. Heat is the form of energy transferred between two systems solely because of a temperature difference. We can feel that thermal energy and observe its effects. But because the energy itself is invisible and constantly dissipating into the environment, capturing an exact measurement of it is a significant engineering challenge. Every material has a unique physical identity called specific heat capacity. This is the precise amount of heat required to change the temperature of one unit of that material's mass by 1 degree. To measure that energy and reveal this hidden thermal identity, we have to force the transfer to happen inside a perfectly controlled trap where nothing can escape. Physicists call this trap an isolated system, a scientific environment where absolutely no heat is allowed to enter from the outside or leak out to the surroundings. In reality, heat is difficult to contain. It constantly escapes through conduction between touching solids, convection within fluids, and radiating electromagnetic waves. This is a 3D schematic of a calorimeter, the tool engineered to stop those leaks. It starts with an inner vessel made of a highly conductive metal like copper, which allows the container and the liquid inside it to quickly reach the exact same temperature. We add a stir made of that same copper. Moving the liquid ensures the entire volume maintains a uniform temperature, preventing the formation of isolated hot or cold pockets. Next, we enclose the copper vessel within an outer wooden jacket. We pack the empty space between them with glass wool to block conductive and convective heat loss to the room. Finally, an insulated lid clamps down, and a highly sensitive thermometer lowers directly into the center of the liquid. Inside this isolated system, a single law applies. The exact amount of heat lost by a hotter body dropped inside will equal the exact amount of heat gained by the colder bodies. By engineering this environment, we eliminate outside variables. The thermometer becomes a direct window into the flow of invisible energy. Let's test this trap by uncovering the unknown specific heat capacity of aluminum, exactly as described in example 10.3 of our physics textbook. We start with a 0.047 kilogram aluminum sphere at 100 degrees Celsius. It's transferred into a 0.14 kilogram copper calorimeter, holding 0.25 kilograms of water, both initially at 20 degrees. Thermal energy flows from the metal until the system reaches thermal equilibrium at 23 degrees. At this point, the energy transfer is complete. With the temperature stabilized, every variable required for our calculation is accounted for. Visualize this balance on a scale. Left, heat lost by the aluminum, its 0.047 kilogram mass, times its 77-degree drop, times its unknown specific heat. Right, heat gained by the water and copper vessel, their masses, times their 3-degree rise, times their known specific heats. Because the system is isolated, we know with absolute certainty these two sides are perfectly equal. Simple algebra solves the equation, revealing aluminum's specific heat capacity. Calorimetry provides a physical demonstration of the universe's law of energy conservation. By tracking exactly what energy is lost and what is gained, we force matter to reveal its deepest thermal properties.